Okay, this is topic 5.2, part 2. We're covering just Kirchhoff's in this video. So we have two equations. The sum of the voltage in any loop equals 0, and the total current into a junction is also 0. So we use Kirchhoff's rules when we're solving more complicated circuits involving multiple loops with more than one battery. So solving a more complicated circuit like this consists of finding the voltages and currents of all of the components in that circuit. So just so we're clear, a junction is a point in a circuit where three or more wires are connected together. The two red dots on the circuit are the junctions. A branch is all of the wire and all of the components connecting one junction to another. So this is a branch. This is a branch in green in the middle, and this is a branch right here. 3 branches in this circuit. And a loop is all the wire and all the components in a complete circle. So in this circuit, I have 2 loops. This would be loop number 1, all this, and this is loop number 2, all of this. So step number 1 in solving a more complicated circuit is to assign a direction of current for each branch. In this case, it's already been done for you, and you should copy the circuit below. We have current coming out of the positive end of this battery and into this junction, and this is I1 as labeled right here. Then we have this current going into this branch, and this becomes I2. I will change the color on this. I2 is going to become I1 once again, right around here. Okay, and I2 can also split because you could have I2 going to the left becoming yellow, or I2 going right becoming I3, which I'll do as purple. Okay, so we have I1, I2, and I3, and those are the directions for current assigned to each branch. If you don't have a good idea which way it flows, if you have a good idea which way current should be flowing, you can choose that idea. If not, just it's a random choice. It will be just fine because in the end we will account for signs. And if with the direction we've chosen, current turns out to be negative, we just take that to mean that the true current is flowing opposite to the arbitrary direction we chose. Okay, so continuing with the rules for assigning current. If current enters a junction, it is counted as a gain and it's given a positive value, a positive sign. If current exits a junction, it's considered a loss and it's given a negative value. So look at this top junction right here. We have an interaction between I1, I2, and I3. I1 and I3 are both positive at the junction. I2 is negative because it's coming out. At the bottom junction, right here, I have an interaction again between I1, I2, and I3. I2 is positive at the bottom, and I1 and I3 are negative because they're coming out. Okay, so from conservation of charge, the sum of the currents at each junction must be 0. This is Kirchhoff's rule for current. So then we will add up the currents and set them equal to 0 and apply the signs accordingly. So for the top junction, we have I2, I1 minus I2 plus I3. That's for the top. For the bottom junction, I2 minus I1 minus I3, and we set both of those equations equal to 0. Next up, we have to handle the voltage in the circuit, so we give each resistor a voltage V and each cell or battery an EMF epsilon. So I'm just labeling these resistors in the circuit V1, V2, V3, and V4. epsilon 1 and epsilon 2 for the two batteries. Please note that cells and batteries increase the energy of the current. Resistors decrease the energy. So we draw some loops. The sum of all the energy gains and losses in each loop must be 0. So these are the two loops. We will end up drawing a direction for the loops, kind of like we did for current. It can be clockwise or counterclockwise, it doesn't matter. Okay? If the loop direction goes in the same direction of the branch current assigned earlier, the resistor energy change is negative. So in purple is the loop, and we can see the arrows corresponding with current are still present. When the direction of the loop, which is purple, matches the direction of the current, that is a negative voltage drop across that resistor. If the loop direction we've assigned goes opposite to the current direction we drew, then the voltage across that resistor is positive. So we can see this would be for V1, is it positive or negative? It's a negative voltage drop. For V2, positive or negative? It's a negative voltage drop. And for V4, is it positive or negative? It is a negative voltage drop. For our loop, we see we have negative QV1 and negative QV2 and negative Q times V4. Remember, charge times voltage gives you energy. Okay, now we look at the voltage for the batteries. So if our loop goes through a cell from negative to positive, the cell energy change is positive. It's kind of like flag football. Wherever the loop last touches, the EMF or the voltage across that loop gets that sign. Sorry. If our loop goes from positive to negative through a cell, the energy change across that battery, across that cell, is negative. Again, kind of like, I don't know, flag football. Whatever you grab at the end, that's what you go with. For our loop, we can see that epsilon 1 is positive, and epsilon, and the energy change across epsilon 2 is negative. So then step 3 is to add up all of the voltages in a loop and you set them equal to 0. Question 1. An electrical circuit is shown with loop X and junction Y. What is the correct expression of Kirchhoff's circuit laws for loop X and junction Y? So the loop includes any component that lies around or touches or faces the loop. So the loop is going around like this, and so I can easily see that the cell that labeled E, R1, and R3 are part of the loop. If I redraw the cell, its positive end is like that, positive is like that, negative end there, and the direction for the loop is like this. So the last thing the arrowhead touches is the negative terminal of the battery, which means that the voltage across the cell is negative for our loop equation. So I have negative E. For R1, it's different. It's a resistor, so we then look at not only the direction of the loop, just like that, but also the direction of current. So because the loop and the current point in the same direction, the voltage across R1 is negative in our loop equation, so that's negative I1 times R1. And then I look at R3, the loop points in this direction, the current I3 goes like that, so that is negative I3 R3. And now I make an equation for my loop X, negative E minus I1 R1 minus I3 R3 equals 0. And if I add I1 times R1 and I3 times R3 to both sides of the equation, I see that I have to eliminate choices C and D because the signs for these loop equations don't make sense. Next, we finish up with the junction Y. The junction Y is at the bottom right-hand side of the circuit. Here is my junction Y. And I just look at the current going in and the current coming out. I1 goes in, it's positive. I2 and 3 come out, that's negative. That gives me an equation for junction Y. I1 minus I2 minus I3 equals 0. And if I add I2 and I3 to both sides, I can clearly see which of the remaining two answer choices is correct. Question 2, last but not least, what is the equation for the dotted loop shown? Okay, so everything within here is contained within the dotted loop and faces the dotted loop, so we will look at the voltages gained or dropped through these two resistors. And I can see that for the 4 ohm resistor, the loop direction points to the right and the current I3 points to the right. So for the 4 ohm resistor, that would make it negative. That's a negative drop. So 4 times I3, that's negative. Then for the 3 ohm resistor, I have the loop is a circle, so it's up like this direction. The direction of the loop points to the left, while the current direction points to the right. That makes it a positive difference, a positive potential difference. 3 times I2, and then I can add these up and set them to 0. I get negative 4I3 minus 3I2, or plus 3I2 equals 0. Now you'll notice I have something that's very similar to that, but not quite. But what matters is for that choice, those two signs are opposite. Let's say in this equation, I decide to add 4I3 to both sides and subtract 3I2 from both sides. I end up with 4I3 minus 3I2 equals 0. The reason IB didn't just give you what you were expecting to get like this is because they want to know, do you understand that mathematically these two are essentially equivalent for Kirchhoff's laws? All right, thanks for watching. That's it.